lesson for the first unit of the Advanced Functions course. This is on characteristics of polynomial functions. In the first section, we looked at power functions, which are single-term polynomial functions. In this section, we're looking at polynomial functions that are made up of two or more terms. And we're going to look at the characteristics of the graphs and the equations of these polynomial functions. So I need to introduce to you a new idea about polynomial functions, and it's about turning points. And turning points we classify as, we call them local min or max points. And those local min or max points may also be absolute min or max points. Let's talk all about that in this first section here. So first of all, let me tell you about a turning point. A turning point, if we look at these two graphs I have on the side here, a turning point is a point where the function switches from increasing to decreasing, or vice versa. So like this point right here is a turning point. Before that point, the function was increasing. After that point, the function is decreasing. So it's a turning point. Same with this point right here. This is also a turning point. And if we look at this function, turning points here, here, and here, 3 turning points. Now those turning points are all what we call local min or max points. Let's look at the definition for local min or max points. They are points that are minimum or maximum points on some interval around that point. So for example, look at, let me zoom in on this a little bit here just to make sure you're clear on what I'm talking about. Now, this point right here, we call that a local max point because on some interval around that point, let me just look at, let's say this interval right here. Around that interval, that point is the highest the function ever goes. So that's what we call a local max point. And yes, the function does go higher than that point over here, but within this little interval I outlined, that is the highest it ever goes. So it's a local max point. And this right here, for the same reason, is a local min point. That's not the lowest the function ever goes, but within that little interval, that is the lowest it goes. So it's a local min point. Now, local min or max points could also be classified as absolute max or min points if they are the greatest or least value attained by a function for all values in its domain, not just around an interval around that point. So for example, if we look at this function down here, this is a local min, this is a local max, this is a local min. But this local min down here, this one right here, this is also an absolute min because not only is that the lowest point the function ever goes in, let's say, that interval, it's also the lowest point the function ever goes. The function is never below that point. So that point is a local min and an absolute min. With that information, let's fill in the blanks here. So let's look at this first graph right here. The point -1, 4, this point right here, is a local max. And the point 1, -4, the point right here, is a local min. We already talked about that. Neither of those are absolute min or max points because there are other points on the graph of the function that are smaller and greater. Sometimes local min and max points are called, and we already talked about this, they are called turning points. And that's how we're going to refer to them a lot. We're going to talk about number of turning points polynomial functions have. On this graph, if we look at this blue one, let's just look at how many local min or max points there are. I've already outlined them before, but let me show you again. There are 1, 2, 3 local min or max points. Of those local min or max points, how many of them are local mins? This one and this one. 2 of them are local mins, and 1 of them is a local max, this one. One of the local min points is also an absolute min, and it's labeled for you right there. Now that you know the new terminology about local min or max points, also called turning points, and absolute min or max points, let's fill out a chart where I give you a graph and an equation of a function, and we're going to comment on its degree, its leading coefficient, its end behavior, how many turning points it has, and how many x-intercepts it has. The reason why we want to do this is because we want to find the connection between the degree and the leading coefficient and figure out how that connects to the number of turning points the function has and how many x-intercepts the function has. That's our goal, so keep that in mind as we go through this chart. So for the first row, the function we can tell from the equation it's degree 2 because that's the highest degree term, and that means it is an even degree function. The leading coefficient, even though we don't see it, we know it's +1. And the end behavior, let's use quadrant notation for the end behavior. It starts in quadrant number 2 and it finishes in quadrant number 1. So we can say from quadrant 2 to quadrant 1. How many turning points does this function have? It looks like it only has 1 turning point right there. Before that point, the function is decreasing. After, the function is increasing. So that's a turning point. So it has one turning point. And how many x-intercepts does this function have? It crosses the x-axis here and here. It has two x-intercepts. Let's complete two more rows together, and then I'll get you to try the rest on your own. So row number 2, we have a degree 4 function. So it's degree 4. So it's another even degree polynomial function. Its leading coefficient, so the coefficient of the highest degree term, is 3. So positive leading coefficient, even degree polynomial, tells us that it's going to have an end behavior the same as the first row, Q2 to Q1. And if we look, yes, it starts in quadrant 2, finishes in quadrant 1. So it goes from Q2 to Q1. How many turning points does this function have? I see 1, 2, 3 turning points on that function. And how many x-intercepts do I see? I don't see any x-intercepts. There are no places that that function crosses the x-axis. Let's do one more together. This polynomial function is degree 3. That's the highest degree term. So this time we have an odd degree polynomial function. Its leading coefficient is 1. Positive leading coefficient, odd degree. That's going to go from quadrant 3 to quadrant 1. How many turning points does this function have? It turns here and here, so there are 2 turning points. And how many x-intercepts does it have? It looks like it has 1, 2, 3 x-intercepts. All right, hopefully you get how we're filling this out. There are 6 more for you to fill out. So pause the video now, try and fill out the remaining 6, and then I'll quickly show you the answers to them after you've tried it. So pause now. All right, let's take up the remaining 6. So just check with your answers as I go through the solutions to this. So I'm just going to fill out the solutions quick and consult with your answers as I go here. Okay, hopefully you did all right with that. One key mistake people make is that for a function that does this kind of little change in rate of increase or decrease, they sometimes misinterpret that as a turning point. But let me just zoom in on this function a little bit for you here so we can analyze it a little more closely. This function here, it doesn't have any turning points. Now the rate of decreasing does change, but this function over its entire domain is decreasing. It never switches to increasing. Since there is no switch between decreasing and increasing, there are no turning points. Let's summarize the findings. My goal is for you to be able to see the equation of a function in standard form, know its degree, and then from that information, understand how many x-intercepts it could have and how many turning points it could have. So let's take a look back at all of these functions, and let's look at the connection between the degree of the function and how many turning points it could have. So the first row, a degree 2 has 1 turning point. A degree 4 has 3 turning points. A degree 3 has 2 turning points. A degree 4 has 3 turning points. Degree 6 has 5 turning points. Degree 5 has 4 turning points. Degree 5 has 2 turning points. Degree 3 has 0 turning points. And degree 4 has 1 turning point. What's the most number of turning points a degree, let's say, n function could have? So like a degree, let's say a degree 6 function. How many turning points could that have at most? Notice the relationship between degree and turning points. The number of turning points was never more than 1 less than the degree. Degree 4 had 3, degree 3 had 2, This degree 5 had 2, but the number of turning points was never more than 1 less than the degree. So a degree n, we say, has at most n minus 1 turning points. Now let's look at the relationship between the degree and the x-intercepts. Degree 2 had 2 x-intercepts. Degree 4 had 0 x-intercepts. Degree 3 had 3 x-intercepts. Degree 4 had 4 x-intercepts. Degree 6 had 2, and so on. You can look through the rest. But at most, a degree n function can have n x-intercepts, up to as many as the degree of the function. There's a couple more particular rules I want you to understand as well. If a polynomial is odd degree, it has to have at least one x-intercept. Why is that? Well, remember, odd degree polynomial functions, let me just show you a quick graph. Let me label the quadrants 1, 2, 3, 4. Let's say we have an odd degree and positive leading coefficient. I know that means it has to start down here in quadrant 3 and finish up here in quadrant 1. Since it has opposite end behaviors, in order to get from here to here, you have to at some point cross the x-axis at least once. That's why it says if it's odd degree, it has to have at least one x-intercept. And at most, it can have up to its degree. If a polynomial function is even degree, though, it doesn't have to have any x-intercepts. Let's look at this. Let's say we had even degree positive leading coefficient. We know that means it would go from quadrant 2 to quadrant 1. So to go from here to here, it does not have to cross the x-axis. It can do anything else above the x-axis, but it doesn't actually have to cross. So if we have an even degree polynomial function, it does not have to cross the x-axis. Therefore, it doesn't have to have any x-intercepts. And then down here is just a summary about end behaviors. And we already know about end behaviors when we worked with power functions. It's the same rules. If we have an odd degree polynomial function, and it has a positive leading coefficient, it goes from 3 to 1. Negative leading coefficient flips it upside down, 2 to 4. If we have an even degree polynomial function with a positive leading coefficient, it goes from 2 to 1. And if we flip it upside down with a negative leading coefficient, it goes from 3 to 4. And beneath, I have graphs that show you what those could look like with lots of different variations of turning points and x-intercepts. But notice all the functions on the same graph have the same end behaviors. Okay, let's actually do a couple examples here. Example 1, describe the end behaviors of each function, the possible number of turning points, and the possible number of zeros. Now, we're not going to comment on how many they have. We wouldn't be able to know that when it's in standard form like this. We would have to get it into factored form, which we'll learn to do later in the unit and next unit as well. But right now, we just want to talk about how many x-intercepts or turning points could it have. And we'll use these characteristics to sketch a possible graph. Actually, I've given you the sketches of the possible graphs, but I just want you to be able to look at the equation and have an idea about how many x-intercepts and turning points it could have. Let's start by describing the end behavior of this one. So this function, it is odd degree. So I'm going to write odd degree. And it is a negative leading coefficient. That's what negative LC means, negative leading coefficient. So based on that information, odd degree negative leading coefficient, I know that its end behavior is going to be from Q2 to Q4. And let me just show this to you in Desmos as well. Now, we of course don't have the graph of this, but notice I have Desmos just showing me the end parts of the graph. Yes, it does start up here in Q2 and it does finish down here in Q4. I have it intentionally not showing us the in-between part. But just based on the equation, we knew for sure the end behavior. How do we know what it looks like in between? Well, we're not going to know for sure it does this, but we should be able to come up with a list of possibilities for how many turning points and x-intercepts it could have. And we're going to list them. So possible number of x-intercepts. At most, since it's degree 5, the most number of x-intercepts it could have are 5. And the least number of x-intercepts it could have, well, let's think, can it have 0? If it's going to start up here and finish down here, it has to cross the x-axis at least once. So we're going to have at least one x-intercept. So it could be 5, or any other number down to 1. 5, 4, 3, 2, or 1. Any of those are possibilities for a degree 5 polynomial function. We don't know which one it is. And like I showed you, it actually is this function. So it actually only has one, which we have in our list of possibilities, but it could have had anything in between. Okay, now let's talk about possible number of turning points. So we learned earlier that the most number of turning points a function can have is one less than its degree. So a degree 5 polynomial function at most could have 4 turning points. What else could it have though? Could it have 3? Let's think about that. So I just pasted a screenshot of the graph with its end behaviors. I'm wondering, can it have 3 turning points? Can this function have 3 turning points? Well, let's think. At most it could do is to have 4 turning points. It could turn once, twice, 3 times, 4 times. That's the most number of turning points it could have. Could it have 3? Can I turn 3 times and have this end behavior? Let me turn once, twice, 3 times. Oh, now I'm going the wrong way. There's no way with the function going in this direction it can finish down here. So it can't have 3 turning points. And if you think about that fully, any odd degree polynomial function would have to have an even number of turning points for it to have the correct end behavior of finishing on opposite sides of the x-axis. And I put that note here for you. Odd degree functions have to have an even number of turning points. So at most it could have 4 or any even number less, 2 or 0. Let's do another one. Oh, and here are some possible graphs of functions that have different combinations of those number of x-intercepts and those number of turning points. Like for example, this one has no turning points and 1 x-intercept, so it met that criteria. Now this function has one specific graph that matches it, and I showed that to you, but we don't know that just based on the equation in standard form. We just list the possibilities. Part B. So this one is even degree positive leading coefficient. That tells me that it goes from Q2 to Q1. And then we want to comment on what are the possible number of x-intercepts and the possible number of turning points. Let's have a look at the Desmos graph with the end behavior shown for us again. So I have the end behavior shown for you. I haven't revealed in between the end behavior. This is what it actually looks like in between. But just based on the degree and the sign of the leading coefficient, we were able to know that end behavior is from 2 to 1. And we should also be able to list the possibilities for what could happen in between, not necessarily knowing that it's actually just going to have 1 turning point and no x-intercepts. What are the possibilities? Possible number of x-intercepts for degree 4. Well, at most it could have 4 x-intercepts, or any number less. Do we include 0? Can an even degree polynomial function have 0 x-intercepts? Look back to the graph. Can I get from here to here without crossing the x-axis? Yes, of course you can. And in fact, this one does exactly that. It never crosses. So 0 is an option for even degree polynomial functions. Turning points. Even degree polynomial functions have to have an odd number of turning points. And I just pulled the screenshot over here again, and just to prove that to you that they have to have an odd number of turning points, if I'm going to start here and finish here, the function has to turn at least once, right? It can't just continue in this direction. It has to turn up going this way. So it has to turn once, but couldn't turn twice because then it's going the wrong direction again. But it could turn 3 times. Now it's going in the right direction. So it has to have an odd number of turning points if it's an even degree polynomial function. So possible number of turning points for degree 4 is at most 3 or any other odd number less. So 3 or 1. And here's some graphs of different combinations of those number of x-intercepts and turning points. Just from the standard form, like I was saying, we wouldn't know which one it is, but we would know what the possibilities are. In order to know for sure what it looks like, we would have to be able to get the function into factored form, and we'll learn to do that later. Example 2, fill out the following chart. So based on the degree, how many x-intercepts could it have, how many turning points could it have, and list all the possibilities. Degree 1, so odd degree. Odd degree polynomial functions have to have at least 1, so they can't have 0 x-intercepts because they have to cross, they have opposite end behaviors. And at most, it can have up to its degree in number of x-intercepts. So the only option here is actually, it has to have 1 x-intercept. Number of turning points, well, degree 1 functions are straight lines. They don't have any turning points. Degree 2 functions, well, those are parabolas. You know what those look like. Possible number of x-intercepts. It can have at most up to its degree, or any number less. And we include 0 for even degree polynomial functions. A quadratic, a parabola, does not have to cross the x-axis because it has the same end behavior. Possible number of turning points, at most it can have one less than the degree, and in fact that's the only option for a quadratic. A parabola has a vertex, it has one turning point. Degree 3. A degree 3 function, odd degree, it has to have at least one x-intercept, and at most it can have up to its degree. So it could have 3, 2, or 1. It cannot have 0 because of the opposite end behavior. It has to cross the x-axis at least once. And number of turning points, degree 3. At most it could have is 1 less than the degree, or any even number less than that, so 2 or 0. Degree 4, number of x-intercepts. At most it could have is equal to its degree 4, or any number less. And we include 0 this time because degree 4 starts and finishes on the same side of the x-axis. It doesn't have to cross. Number of turning points at most is 1 less than the degree, so 3, or any odd number less, so 3 or 1. Degree 5, possible number of x-intercepts, 5, 4, 3, 2, or 1. We cannot include 0. Odd degree starts and finishes on opposite sides of the x-axis, so it has to cross at least once. Possible number of turning points at most is 1 less than the degree, or any other even number less, 4, 2, or 0. Okay, hopefully you get these connections now. And let's try and connect some graphs to equations. Now, example 3 tells you to do a lot of things. It tells you to talk about the key features, talk about possible number of turning points, and all these kinds of things. But I don't think I want to go that in depth for this example. I just want you to match up the equations to the graphs. And we should be able to do that just by looking at end behavior. So for this example, let's just pay attention to what the end behavior of the graph is, and then be able to figure out what equation does it match to. Well, let's look at equation A, odd degree, positive leading coefficient. So equation A, odd degree, positive leading coefficient. So you should know by now, odd degree positive leading coefficient means it goes from Q3 to Q1. And then let's find what graph does that. Which graph goes from quadrant 3 to quadrant 1? Well, there's only one of them. This one right here goes from quadrant 3 to quadrant 1. So graph 4 matches with that equation. Equation A matches with graph 4. Let's do B. B is even degree, negative leading coefficient. Even degree, negative leading coefficient. We know that means it goes from quadrant 3 to quadrant 4. Which graph goes from 3 to 4? This one right here, graph number 1. So graph number 1 matches equation B. Equation C. Equation C, odd degree, negative leading coefficient. So that means it goes from 2 to 4. Let's find the graph that goes from quadrant 2 to 4. It's this one right here, graph number 3. Part D, even degree, positive leading coefficient. That means it goes from quadrant 2 to quadrant 1, and we could have done this one by process of elimination, but quadrant 2 to quadrant 1, that's this one right here, it's graph number 2. Okay, we have one last section in this lesson, and this is learning about finite differences. So for a polynomial function of degree n, where n is a positive integer, the nth differences will all be equal. They'll have the same sign as the leading coefficient, and we can actually calculate what they would be equal to by doing a times n factorial, where a is the leading coefficient. Now, I just said a lot of stuff there. I'll go through it. But first, maybe what you might be wondering is, what is this notation? That's a factorial notation. And what that means, if we look over here, 5 factorial means 5 times 4 times 3 times 2 times 1. And 7 factorial would mean 7 times 6 times 5 times 4 times 3 times 2 times 1. I think you get it based on that. Let me also remind you about kind of what finite differences are. So let me take you back to like grade 9 and grade 10. So remember in grade 9 you worked with linear relations, like let's say the function y equals 3x. And if we made a table of values for that function, x, y, let me just pick some values for x, and then calculate the values for y by subbing them in. If I were to calculate the finite differences, so the differences in consecutive y values, where the difference in x values is constant, I would do always bottom minus top. 3 minus 0 is 3, 6 minus 3 is 3, 9 minus 6 is 3, 12 minus 9 is 3. Those are called the first finite differences, the first column of finite differences. They would all be constant if you have a linear relationship. Then grade 10, you learned about quadratics. Let's say we had the function y equals 2x squared. Let me pick the same set of x values, sub in. If you found the first differences for a quadratic function, so 2 minus 0 is 2, 8 minus 2 is 6, 18 minus 8 is 10, and 32 minus 18 is 14. Notice those finite differences are not constant. But if I were to find the second finite differences, the differences in these values, 6 minus 2 is 4, 10 minus 6 is 4, 14 minus 10 is 4, the second finite differences would be constant because it's degree 2. And a degree 3 polynomial function would have the third differences all constant. And a degree 4 polynomial function would have the fourth differences all constant, and so on. So what this section is telling you, it's telling you that for a degree n polynomial function, the nth differences will be equal, like I just showed you. They will have the same sign as the leading coefficient. Notice these 4's were positive. They have the same sign as that, which is positive. And they're equal to, so the reason why this is 4 specifically is because they're equal to a times n factorial, where a is the leading coefficient and n is the degree of the polynomial function. So for this one, I mean, they're both 2, so maybe it's not a great example, but the finite differences would be equal to a, the leading coefficient, multiplied by the degree factorial. 2 factorial is 2 times 1, which is just 2, so we get 4. There we go, 4. So let's do an example with this set of values. So we don't have the function this time. I just gave you a table of values that show the relationship between x and y. From that table, we want to figure out the degree of the polynomial function, and the sign of the leading coefficient, and the value of the leading coefficient. So the degree of the polynomial function, we'll have to figure out which finite differences are all going to be equal. So we'll keep going until we get a row of finite differences that are equal. So the first row, now notice the x values are evenly spaced. That's important for this to be able to work. We look at the y values, and we do the bottom y value minus the top y value. Always bottom minus top, or else the formulas that I just showed you are not going to work. So bottom minus top, so we would do negative 12 minus negative 36. That means negative 12 plus 36, which is 24. The next one, negative 2 minus negative 12. And that equals 10. And then after that, 0 minus negative 2, which is 2. 0 minus 0, which is 0. 4 minus 0, which is 4. 18 minus 4, which is 14. And 48 minus 18, which is 30. So those first finite differences are not equal, so it's not degree 1. So we do the second column of finite differences. Always bottom minus top. 10 minus 24 is negative 14. 2 minus 10 is negative 8. 0 minus 2 is negative 2. 4 minus 0, 4. 14 minus 4, 10. And 30 minus 14, 16. Second differences, also not equal. So we find the third differences. Bottom minus top, negative 8 minus negative 14 is 6. Negative 2 minus negative 8, 6. 4 minus negative 2, 6. 10 minus 4, 6. 16 minus 10, 6. They're all 6. So since the third differences are all equal, we know that this is a degree 3 polynomial function that has this relationship between x and y. So it's degree 3. Part B asks, what's the sign of the leading coefficient? Well, since the third differences are all positive 6, we know that the sign of the leading coefficient must also be positive, so it has a positive leading coefficient. Part C says, what is the actual value of the leading coefficient? Well, I told you a formula where it said finite differences equal a times n factorial, where a is the leading coefficient. The finite differences, those, when they were constant in the third column, the finite differences were all 6. So I can replace finite differences with 6. A, we don't know the leading coefficient. And then n, the degree, since it's the third column that are all equal, we know it's degree 3. So we can replace n with 3. And then we solve for a. So 6 equals a times 3 factorial. And 3 factorial is 3 times 2 times 1, which is 6. So a times 6, I can write that as 6a. Divide both sides by 6, I get a equals 1. So the leading coefficient is, in fact, 1. Last example, this time I'm going to give you the equation. And it says, what is the value of the constant finite differences? Well, it'll be the fourth column where they're all constant, but what is the value of those finite differences in the fourth column? We can calculate that just by doing a times n factorial, where a is the leading coefficient, 2, times n, which is the degree. And 4 factorial would be 4 times 3 times 2 times 1. So 4 times 3 is 12, times 2 is 24, times 1 is 24. So 2 times 24, which is 48. If we were to do a table of values for this function to calculate finite differences, we would find the fourth column, they are all equal, and in that fourth column, they would all be 48s. Okay, that's it for the second lesson.